But how about Q enclosed? Well, would Q enclosed still be capital Q? No, because it's only the amount of charge that's enclosed within the Gaussian surface. Well, this portion of the charge is enclosed within the Gaussian surface, but this portion should not be included anymore. So this is where this becomes more complicated. We have to figure out what portion of the total charge is inside of here. So now we can learn how to do that. There's a couple different ways that you could do it. I guess one thing we could do is we could say, we could use ratios and proportionality, since that's what we used last week. So what is it that determines how much charge you have? Well, it's the amount of volume that you're focusing on. What determines this charge over here is the volume that we're focusing on. So we're going to have to figure out a volume here. So let's look up, you might have that in your mathematical appendix. So
4/3 pi r cubed. That one is perfect.
Okay, that's right. And remember, this is the total amount of charge. So we should be using the total size of the sphere. So should that be an uppercase R or lowercase r?
It should be an uppercase.
So that would be one part of the proportionality. And then we have to figure out what goes over here. So we were trying to use Gauss's law here to find the electric field inside this ball of charge. But in order to do that, we need to know what amount of the total charge is enclosed inside our Gaussian surface. We know this entire ball has a charge of Q, but only a portion of that is inside. Well, when we're focusing on the entirety, we have an entirety of charge of capital Q, and here's the entire volume, except you had the formula right, that was 4/3 pi r cubed. Now on this side, we should put a ratio that's about this smaller sphere. So what should I put up here? Well, this is the unknown that we're trying to figure out, the amount of charge that's enclosed. And then what should I put down here?
Is 4/3 pi little r?
That's right. Since this represents the little sphere that's represented by the Gaussian surface, this should be the surface area of that smaller sphere. Like so. There's a couple things we can do now to simplify this equation. What we want to do now is solve this for the charge enclosed. How can we solve this for the charged enclosed? Yeah, that would work. Although, since all we're trying to do is get Q enclosed by itself,
We could just multiply both sides by 4/3 pi.
little r cubed. That's right. That'll cancel out the terms we don't want on this side. What do we have left on the other side? Let's work that out on paper. Good. The 4/3 pi cancels with this 4/3 pi. And we're left with little r cubed over big R cubed times capital Q. Now we know what proportion of the total charge is enclosed within this smaller sphere. I think this is one good way then to find the total amount of charge in a smaller object based on a bigger object, set up a proportion. So on this side we had total charge and total volume, and we compared that to the small charge and the small volumes. This is a good technique you might need in other problems. And you might be able to just go straight to here, though, because basically all we need to know is what fraction of the total volume is represented by this smaller volume. Well, the volume depends on the cube of the radius. So this is, we could go straight to here if it's clear to us that the radius of the ratio of the cubed radii tells you what fraction of the bigger volume is accounted for by the smaller volume. For example, if this volume is 1/3 of this volume, then it should account for 1/3 of the charge. Or if this volume is 1/2 of this volume, which would account for 1/2 of the charge. So you might be able to go straight to here. The big mistake that I think people might make here, though, is just comparing R to R, or R squared to capital R squared. But if you think about it, the total amount of charge depends on the volume, not surface area or just radius. The total charge depends on the total amount of surface. The total charge depends on the total amount of material that's carrying that charge. Since the charge is uniformly distributed here, well, that depends on the volume. So the big mistake people might make here, like I said, is some people here might just put, say, Q over surface area. Well, that wouldn't work, because the surface area is not proportional to the amount of charge. It's the volume that's proportional to the amount of charge. If we double the volume, we double the charge. Doubling the surface area does not necessarily double the charge, because there's charge in many different places besides just the surface. So now we're ready to plug that in over here. So for the enclosed charge, we can put in this term over here. So that's our new enclosed charge. That's really the only thing that's different from the previous case that we did. The previous case that we did was the point that was outside the ball of charge. Well, the only thing that's different is that it's harder to find the enclosed charge. All right, and now we're ready to solve for E. Remember that our goal all along here is to solve for E. So let's use some algebra and work this out on paper and get a single expression for E. That's good. So some of the little r's cancel. These little r's cancel with the little r's on top. We're left with a single power of little r on the top. Is what you got?
Yeah.
Good. Now, I think it turns out that it's more conventional to write this equation in terms of k. So how could we rewrite this in terms of k?
KRQ over RQ.
Yeah, remember that k equals 1 over 4 pi epsilon 0. K equals 1 over 4 pi epsilon 0. So we can just take out the 4 pi epsilon 0 and replace that with k. 1 over 4 pi epsilon 0 and replace that with k. So now we're ready to answer the question. The question was asking us to find the electric field at all points in space. And when we thought about it, we saw there was really two different cases. There was the case when we were inside the ball of charge, and the case when we were outside the ball of charge. So we got two different formulas for those two different cases. You could write these formulas in terms of epsilon 0, but it's more conventional to write these particular formulas in terms of k. Depends on the situation, I guess, but I ended up writing them in terms of k. So this would be the complete answer. The big point here was that the electric field depended only on the enclosed charge. Well, when we were inside the sphere, not all of the charge was actually enclosed inside the Gaussian surface. So that was why we needed a different formula when we're inside the ball, because we didn't want to take into account all of the charge, only a fraction of it. I think a lot of people that did this problem wouldn't even think about this case. So it's important when they ask you for the electric field everywhere to think about really everywhere, including inside the object. And you're pretty likely to see a problem like this on the exam. This is a pretty typical type of problem, so you want to think about that. You can see how crucial it is to be very clear in your mind about the difference between little r and big R here.
Yeah.
Little r is the point in space that we're focusing on, where that's the point that we're going to draw the Gaussian surface through. And big R represents the actual ball of charge, or object that's got the charge on it.